recording. All right, hexadecimal notation, for those of you who are not super familiar with hexadecimal notation. We are representing each letter or number as a binary string, 4 bits. So this is how you can translate from hexadecimal notation to binary. Computer science people, you can tune out for the next, I don't know, minute and a half or so. So you can write things as element 1 through 16, or you can write them using zeros and ones. This is the conversion. If you're interested in why the conversion works, it's not super difficult to figure out, but this is the conversion. In SHA-1, you have both things going on. You have hexadecimal notation going on, and you have binary notation going on. So you have to be able to convert back and forth. For example, if t is between 20 and 39, this was the constant that I had in hexadecimal notation. That's from the previous slide, right? If t is between 20 and 39, that's my constant. I can also turn that into binary notation. So 6 is 0, 1, 1, 0. That's my first block of characters here. E is 1, 1, 1, 0. So we can go back and forth from hexadecimal to binary notation. In the infinite wisdom of the programmers who came up with SHA-1 in the first place, they used both. So you got to be comfortable with both. We've got both hexadecimal and binary, and it's just a conversion back and forth. Okay, there is all the introductory stuff. Again, taking notes live today is you're going to be rushed. Here we go. Let's talk about the actual algorithm, and it's going to get even more complicated. Here's what we've got. So we're going to start with the message M. Here's where we're starting, message M. We are going to divide message M into blocks, and each of these blocks is going to be 512 bits. 512 bits, and if you don't have a message length that is easily divisible by 512, then you pad the message at the end. And there are protocols for how you pad SHA-1. There's standard ones there. So I am going to divide this. We're going to say we have L blocks all together. So blocks into messages of 512 bits. If you divide 512 by 4, you get 128. So each of these blocks have 512 bits. They have 128 hexadecimal characters because each hexadecimal character encompasses 4 bits. We've got 128 hexadecimal characters or 512 bits. We also need these things called initial values. So these are my initial values in hexadecimal. There are 5 of them, H0 through H4. These, if you stare at them, look less random than the constants that I had previously, and you should be able to see some patterns here if you stare at these. 6, 7, 4, 5, 2, 3, 0, 1. Patterns are going on there. E, F, C, D, A, B, 8, 9. We've got some patterns going on there. 9, 8, B, A, D, C, F, E. You can see the patterns, etc. So these are the initial values that we need for SHA-1. Okay, that's the setup. Here's how the algorithm works. So remember what we're doing. Think big picture. We are taking a message block, and then we're taking the input, we're taking a message block, and we're taking the output from the previous one. We're putting them into this function, and we're getting out an output. We're taking that output and the next message block, we're putting them into this function and doing this again. That's the process here. So here's how that's going to work for a message block. I want to write this message block as W0 through W15. Each W sub J has 32 bits. So we've got 16 message blocks of 32 bits each. If you do some multiplication, 16 times 32 is 512. That makes sense because last time we said we were going to divide the message blocks up into 512 bits. So we've got 512 bits. Also, if each of those has 32 bits, when you divide by 4, they have 8 hexadecimal characters, right? 4 bits to 1 hexadecimal character. So we are writing this message as a sequence of 16 blocks. Each of those blocks has 32 bits or 8 hexadecimal characters. Okay. So that's T equals 0 through 15. T equals 16 through 79. So we are going to generate a whole bunch more of these. This is what we're going to do. We're going to do a bunch of exclusive ORs. So we're going to generate a whole bunch more of these by doing some exclusive ORs, and then at the very end doing a rotation, because why not? We've got enough going stuff here. We also have a rotation. So we've got these first 16 W's that come from our message, and then we've got the rest of them that also come from our message because they are using these previous values. So this is what's going on here. Okay, now we've got these things called registers. Told you today was going to be very heavy on the protocol. We've got these things called registers, and they need to have an initial value. So the registers are labeled A through E. I'm going to show you a picture in just a second, and hopefully that will make this a little bit better. So the registers need initial values. These are those H0 through H4 that I had on the previous slide that kind of sort of had a pattern to them. So those are my registers. Let me pause and show you a picture and show you what's going on here. Where's my picture? Okay, so here's what's happening. We've got these registers up here, A through E. They're just basically, I can put a value into them. So I have these initial values, H0 through H4, that are going to go into these registers initially, okay? That's the first thing that's happening. We've also got this message that we divided up into W0 through W15, and then we generated these whole bunch of other values, W16 through W79. I'm going to back up for a couple of slides, talk about what is happening here, and then we are going to talk about how we get an output. But here's where I'm at. I've got these registers up here that have these initial values assigned, and I've got these values of W0 through W79 that have come through my message. How are we doing? Today is super heavy on the protocol, and if I could see you all in class, I could see your reactions better. Kinda, sorta, mostly, sorta, kinda, okay? Kinda, okay. All right, let's back up. All right, here's where we're at. So now we're going to do an iterative process, right? Remember I said this was an iterative process. So we're going to write a for loop. Computer science people, you should think about how you're writing this for loop. So we are going to run this loop for T0 through 79, and we're going to assign new values to the registers. So right now I've got values in A, B, C, D, E. We're going to do a bunch of math, and we're going to get new values in A, B, C, D, E. Here's how. So I've got this temporary value, whole bunch of stuff going into here. It's the value in A rotated by 5 bits plus the value in B, C, and D plugged into this function. And remember, if we back up, we had 4 different functions that we were working with, right? Going back here, we had 4 different functions that we were working with. There they are. So the function is going to change as we continue to repeat this process. The function's going to be the same for the first 20 iterations, and then the function's going to change. And then it's going to change again, and then it's going to change one more time. So this function changes as we work through all these iterations. Okay. So we are adding to that the value in that register E. We're adding to that the WT value. So this is what came from my message, right? We broke our message up into W0 through W15, and then we generated all the rest of these W values. And we are adding to that the value of K sub T. That was those constants that didn't look like they had any pattern at all whatsoever. And again, these values of the constants are going to change as you go through this process for t equals 0 through 79. So we're generating this temporary value of t. Okay, let me show you that on the picture. Here we go. So look at what's happening here. I'm taking A and shifting it by 5. That's the first thing that's happening. Taking A and shifting it by 5. Taking A and shifting it by 5 on my picture. Do we see that? Yes. Taking A and shifting it by 5. Yes, good. Okay, we are taking B, C, and D and putting them into this function. We are taking B, C, and D and putting them into this function. Do we see that on the picture? Taking B, C, and D and putting them into this function. This is just for a specific value of t, so it doesn't have f sub t labeled, but that's okay. All right, we are next adding E. So this uses this symbol for addition here. So we are taking E and adding it. We are taking that and adding it to the function that had B, C, and D coming out. This is my second addition on the previous slide. That's this addition right here, my second addition on the previous slide. To that, we are adding the value of A that we had rotated. This is my first addition on the previous slide. I'm taking the value of A that I had rotated and adding that to here. So we see those? All good? Okay. I have this W sub T value that I am adding. I've got this W sub T value that I'm adding. So that's my addition right here. This W sub T value that I'm adding is my addition right here. I've got this K sub T value that I am adding. So that is this addition right here. I've got this K sub T value that I'm adding. Okay. Does the picture help? Hopefully, maybe, kind of, sort of, a little bit. All this stuff is going in. Okay, so this thing right here is what I'm calling T. This is my temporary value. And then remember what we have to do. We have to assign new values to the registers. So here's how I assign new values to the registers. I'm going to take that temporary value and put it into A. I'm going to, take that temporary value and put it into A. Taking that temporary value and putting it into A. Whatever was in A, I'm going to put into B. Whatever was in A, I'm going to put into B. Whatever was in A, I'm going to put into B. Whatever was in B, I'm going to rotate by 30 and put into C. Whatever was in B, I'm going to rotate by 30 and put into C. Whatever was in C, I'm going to put into D. Whatever was in D, I'm going to put into E. Whatever was in C, I'm going to put into D. Whatever was in D, I'm going to put into E. So that's my new values of these registers. Good-ish, kind of, yes, okay. So this process gets repeated 80 times. I start with those values, H0 through H4 in my registers. I use this function, I use the rotation, I add stuff mod 2 to the 32nd, and I get new values in my registers. Then you can think of those new values in your registers as bumping up to the current values in your registers. You say t equals 1, and you do it again. And then you say t equals 2, and you do it again. You say t equals 3, and you do it again, all the way through t equals 80. All right? The function is changing as the value of t changes. So once you hit t equals 20, then you've got a new function going on here. The value of k sub t is changing as t goes up. So once you hit t equals 20, you've got a new constant going on here. The value of w sub t is changing every single time. The first 16 of those come from your message, and then the rest of them are the ones that you have generated. Yes? Good? Kind of? There's a lot going on? Okay. So then, now that we've got this, how do we actually output a hash value? Daniel, question first.
And so each time it goes through it, is that called a round? Is that
Yes.
what they call, like?
Yep, so I'm gonna iterate this. I'm gonna compute 80 rounds is what's gonna happen. Yes,
Okay.
yeah. Okay, once we do all that, remember what we're trying to get. We are trying to get a hash value out for this function. So how do we do that? How do we do that once we've processed all the blocks? I'm going to do some values here. So H0 is going to be my original H0 plus whatever value I have in register A. Same thing for each of these. H1 is my original H1 value plus whatever I had in B. If you're a mathematician, these equations make you crazy. If you're a computer scientist, they are totally and completely okay. These equations make me crazy, but it's kind of like an assignment. So I am saying my new H0 is my old H0 plus A. I really hate these equations, but computer scientists are fine with them. H1, my new H1 is my old H1 plus B, etc. So we've got all of these. And then, yay, we're ready for the final output of the hash function. It is all of those concatenated together. So remember that each H is 8 hexadecimal characters, 32 bits long. So the hash value is 160 bits, or 40 hexadecimal characters. Each of these has 8 hexadecimal characters, so your hash is going to be 40 hexadecimal characters. That's how long your hash is. Okay, summary. So here's what's going on. We have our message divided up into blocks. We repeat this process for each of the blocks. We do it 80 times. We get values out. We take our initial values. We add them to the final output in the register, and that is our hash function. Yes, today demonstrates why I am not a computer scientist, because I can talk about this and it is fine, but this is a really, yeah, okay. Elijah, yeah.
So just to be clear, you only assign those registers like initially once, like you keep them, they pass to the next block when you're computing the next block, right? So
Correct.
when you go from W0 to W1, you're keeping those registers.
Yes, exactly.
Okay.
Yes, they pass through. Yes. Other questions or computer science people, other things that you would say differently from what I said, which is completely and totally acceptable. Again, I'm talking about this from a mathematical point of view. John, yeah.
I mean, you said it both ways, but the rotation versus shifting, I think we would normally say shifting, but also just another thing to note, I think on those assignments, it would probably be important what order you did them in if you're actually looking at the overwrite past values in the registers.
Okay. Yep.
I know it doesn't really matter for anyone, but yeah.
Right. Nope, it totally does. And you're right. We can either talk about shift or we can talk about rotation. Either way. You would probably say shift?
Correct.
Okay. And I would say the reason, again, thinking about rotation, because the stuff at you rotate to the left. So the stuff at the beginning goes to the end. Either way, doesn't make a difference. Either way is totally fine. Two different ways of talking about it. Other ones, Elijah, yeah.
Well, I was just going to say, I don't think it exactly is a shift, because shifting...
Oh, because it carries over.
Yeah, because it carries over.
Yeah,
so
okay.
Shifting actually just puts zeros on all the ones that it moves over.
Oh, okay. So this really is a rotation then, because you have
Yeah.
to take the stuff at the beginning and put it at the end. Okay.
So it's not quite a bitwise shift.
Okay.
Hence the 3 left arrows and not 2.
Yeah.
Yes. 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 Other things.
This is just nitpicking,
Go for it.
but it kept on saying bitwise mod 2, but bitwise implies mod 2 because you're working with bits.
Oh, sure. Okay. So I'm being redundant. I'm not being wrong, but I'm being redundant.
Yeah.
Okay. And again, this is why I'm not a computer scientist. I really should have Dr. Schultz guest lecture on today, but that is not happening either. So yes. All right. How we doing? Any other comments? Feel free. Now's a really good time to make them. Anything else? Okay. We are absolutely positively not working through this by hand.